All right, so section 5.2 is on verifying trigonometric identities. So find your sheet, your notes sheet that looks like this, and then as you need to pause the video, go back if you need to repeat, or if something's not making sense, re-listen to it and so forth. But take the time to write your 6 reciprocal identities, your 2 quotient identities, and your 3 Pythagorean identities so that you have them as an easy reference. And the more you write something down, the more likely you'll remember it. So our strategies for today are going to be to verify that something on the left is equal to something on the right, or something on the right is equal to something on the left. So for example, we're going to verify that cosecant squared of theta minus the cotangent squared of theta over the tangent squared of theta times the cosecant squared of theta is equal to the cosine squared of theta. So unlike yesterday, you have a plan of attack. You know what this is supposed to be, your answer is supposed to be. And you want to start by working with the more complicated side of the equation and make it look like the less complex side of the equation. So nothing's going to cross over the equal sign if at all possible. Ask yourself, what do you notice and what does this want to become? And then look for things like greatest common factor or other factoring opportunities, ways to add fractions, getting a common denominator, squaring binomials, using your fundamental identities. And if you get to a point where you don't know what to do, just all else fails, try converting everything to sines and cosines. So we have lots of possibilities here. Let's start by asking ourselves, what do we notice? Well, on this first example, we can see that the left side is definitely more complicated than the right side. So we're going to want to show that the left side is equal to the cosine squared of theta. That's going to be our goal the whole way down this path. And so we can ask ourselves, what do we notice about the left side then? So the left side has a whole bunch of squared things. So if you notice that you have a lot of squared terms, then you might want to start by looking up above and saying, hey, can I use a Pythagorean identity, especially when there's a sum or difference in the squared terms. So we see cosecant squared theta minus cotangent squared theta. Well, that looks a lot like our third trig identity. 1 plus cotangent squared theta is equal to cosecant squared of theta. So if I wanted to get that cosecant squared of theta and bring the cotangent squared of theta to the other side, we'd be subtracting it. Cosecant squared theta minus cotangent squared theta is 1. So we're using a Pythagorean identity here. Can abbreviate, and the numerator is going to become a simple old 1, and the denominator has to stay the same. We don't want to do too many things at one time in one step. So tangent squared of theta times the cosecant squared of theta, 1 over them is equal to the cosine squared theta. So we've done one thing this time. We changed this to 1. Next, we ask ourselves, okay, what is this trying to become? It's trying to become a cosine squared theta. So I have 1 over tangent squared theta times cosecant squared theta in the denominator. And so I can ask myself, what can I do to make this look more like the right? Well, we notice that we have 1 over tangent squared theta and 1 over cosecant squared theta. That's like saying 1 over tangent times 1 over tangent times 1 over cosecant times 1 over cosecant. It's just an abbreviated way of looking at it. So I could use my reciprocal identities to change 1 over tangent squared of theta to a cotangent squared of theta, and to change 1 over cosecant squared of theta to sine squared theta. And that looks a little bit better now. We don't have fractions, but we still don't have what we're trying to get to, which is cosine squared of theta. But I think we're on the right path, because cotangent squared of theta is the same as cotangent of theta times the cotangent of theta. And we have a quotient identity that says cotangent squared of theta is cosine squared of theta over sine squared of theta, or the cosine of theta over the sine of theta times the cosine of theta over the sine of theta. So we can rewrite cotangent squared of theta using a quotient identity as the cosine of theta times itself over the sine of theta times itself. And the sine squared theta is still there, hasn't changed. The only thing that we've changed is we've changed the cotangent squared theta to say it's quotient. And now what do we notice? Well, I see that cosine squared theta. We're trying to get cosine squared theta on the left-hand side in addition to the right. How can we do that? Well, sine squared theta over sine squared theta is simply 1, so cosine squared theta is going to be equal to cosine squared theta when we simplify. Alright, so that wasn't too bad, so let's try another one. We're going to do the same kind of process. We're going to look and decide which side looks more complicated, and let's try to make that equal to the less complicated side. So I think you would probably agree that a fraction plus a fraction is more complicated than a number times two items. So we're going to try to make everything on the left look like 2 times the cotangent of y cosecant of y. So that's our goal. Okay, so the next thing we say is, okay, what can we do? Well, we need to look for opportunities to add fractions, for example. I see a fraction plus a fraction. In order to add 2 fractions together, I need to get a common denominator. I can abbreviate it CD. And so we're going to go try to get a common denominator here. The first term is missing a secant of y plus 1. So if we multiply top and bottom by that, we've multiplied by 1. And the bottom, or the right side, is missing a secant of y minus 1. So we'll multiply top and bottom, numerator and denominator, by secant of y minus 1, which is a 1. So when we do that, now we're going to have a common denominator, and we can put everything over that common denominator. Our common denominator is going to be secant of y plus 1 times secant of y minus 1. And in the numerator, we will have a secant of y times plus 1 times 1, so secant of y plus 1. And the other half of this fraction is the 1 times the secant of y minus 1. So we're going to have a 1 secant of y minus 1. All right, so let's do some simplifying here. When we do that, secant of y plus a secant of y is 2 of these secants of y's. And 1 minus 1 is 0. And let's simplify the denominator by distributing everything out. Secant of y times a secant of y is a secant squared y. Secant of y times a negative 1 is a negative secant of y. Positive 1 times secant of y gives us a positive secant of y, so they are gone. This is like a difference of squares, the factored form, and then 1 times a negative 1 is going to be a negative 1. Well, that looks better because now we see this 2 that we're trying to achieve. So now we ask ourselves, what do we notice again? Well, anytime we see a sum or difference with a squared term, we want to start thinking about Pythagorean identities. So up here in our Pythagorean identity, we can see secant squared of theta is tangent squared of theta plus 1. If I move that 1 to the other side, so it's a secant squared theta minus 1, then that should be equal to the tangent squared theta. So if we want to use this Pythagorean identity, we can substitute a tangent squared of y in the denominator and keep our 2 secant of y in the numerator, one change at a time. All right, so that's looking better. We see the 2 that we're trying to achieve, but we're missing a cotangent and we're missing a cosecant. Instead, we have a tangent squared in the denominator and a secant in the numerator. But if you think about it, 2 over the tangent times the tangent is like a 2 times a cotangent, right? We could use a reciprocal identity, to get a 2 times the cotangent of y, we're just using one of these tangent squareds, times this secant of y that's staying the same over a tangent of y. That helped us get a 2 cotangent of y. One of these tangents became a cotangent when it came to the numerator. It's the reciprocal identity. So what can we do now to make secant of y over tangent of y become the cosecant of y that we're trying to achieve? Well, remember that statement that said, hey, if everything else fails, maybe try converting everything to sines and cosines. So let's leave the 2 cotangent of y like it is. It's what it wants to become. But the secant of y is the same thing. The secant is the reciprocal of cosine. So let's rewrite secant of y as 1 over cosine of y. And let's write the tangent of y, or 1 over the tangent of y. That's the cotangent of y. Cotangent of y is the same thing as cosine of y over sine of y. So we used I guess two things here. We used a reciprocal identity in addition to a quotient identity. So we did two things at once, which is kind of violating the rules a little bit. We want to try to do one thing at a time, one per row. But I think that helps you see that the cosines are going to cancel or simplify. And that can help us see that now we have a 2 cotangent of y times a 1 over sine. And the 1 over sine is the reciprocal of, so 1 over sine is the reciprocal of cosecant. And that's what we're trying to achieve. 2 times the cotangent of y times the cosecant of y is 2 times the cotangent of y times the cosecant of y. All right, our next example has a lot going on as well. We're trying to get cosecant squared of theta minus 1 times the quantity cosine squared theta minus 1 to be equal to a negative cosine squared of theta. So this side is definitely the easier side, the simplified side. So we want to make everything look like this. So our goal is to get negative cosine squared theta. All right, so what do we notice? Well, I notice that we have some squared terms and sums and differences. So let's think about what cosecant squared of theta minus 1 looks like. If I go up here and see cosecant squared of theta, if I subtract the 1 from both sides, cosecant squared theta minus 1 is going to be cotangent squared theta. So I can use a Pythagorean identity to say cotangent squared theta in place of this guy. And cosine squared theta minus 1. Okay, cosine squared theta minus 1. If I brought the 1 to the other side, if I subtracted 1 from both sides, then I'd have sine squared plus cosine squared minus 1 equals 0. But let's move that sine squared to the other side. So another way of thinking of this is cosine squared theta minus 1 is the same thing as a negative sine squared theta if we subtract sine squared theta from both sides. So this becomes a negative sine squared theta. So we're taking cotangent squared theta times a negative sine squared theta. Well, that looks better. It's a lot less complicated, but still not as simple as negative sine or negative cosine squared theta. So where can we get a negative cosine squared theta? Well, hopefully you're recognizing that cotangent squared theta has a quotient identity. Cotangent squared theta is cosine squared theta over sine squared theta. So we can rewrite this as cosine squared theta over sine squared theta times a negative sine squared theta. Oh, that looks good because we get our negative here. And what happens when we are multiplying cosine squared theta times a negative sine squared theta and dividing it by a sine squared theta? Our result is going to be a negative cosine squared theta because we can cancel factors, so simplify. Can't cancel sums and differences, but we can cancel factors, things that are multiplied together. All right, two last examples. The next one says, let's take the secant of x minus the cosine of x and make it equal to the sine of x times the tangent of x. So you could debate whether subtracting is more complicated than multiplying. I would say, yeah, most likely your subtraction problem could be considered more complicated than multiplying because we can do a little bit more with this. So you could work either way. Let's start with the left side and see if we can make it look like the right side. So maybe we want to get maybe we want to get rid of the secant and change it into sines and cosines. So let's do a reciprocal identity because secant is 1 over the cosine. All right, that's definitely more complicated than it was just a moment ago. And we're trying to make it less complicated, but now we have a fraction that we are subtracting a number, a whole number from, or a unit, a term from, and so let's get a common denominator. It's usually a good idea when you have fractions. So we'll have a common denominator of cosine of x. So in order to get a common denominator of cosine of x, our second term needs a cosine of x if we multiply by the top and the bottom, or the numerator and denominator, by cosine of x over cosine of x. We're multiplying by 1, and that doesn't change the actual function, just its appearance. So we will have 1 minus cosine times cosine is cosine squared of x now in the numerator, and in the denominator we have a simple cosine of x. All right, still not simpler than sine x tangent x. And there's not one right way to do this. You could have worked with the right side and made it become the left side. But hopefully you're starting to notice that we have a sum or difference here and a cosine squared, so this is likely a Pythagorean identity. So we remember that sine squared plus cosine squared equals 1. So if we subtract cosine squared from both sides, sine squared of theta will be 1 minus cosine squared of theta. So 1 minus cosine squared theta by a Pythagorean identity is going to be sine squared theta. And that sine squared theta is over cosine of theta, or cosine of x, my apologies. And so I don't want to switch variables on you in the middle of everything. Do a real quick erase here. All right, so we still want that to look like a sine of x times the tangent of x. I see the sine of x, but I see an extra sine of x over a cosine of x. But wait a minute, isn't the sine of x over the cosine of x the same thing as the tangent of x? Yes, that's a quotient identity. So we have one sine of x that we want to keep as it is, and the additional sine of x over cosine of x becomes a tangent of x. Left side equals the right side, so we verified it. That's the benefit of working with these problems, is you know what your goal is, you just have to find a way to get there. All right, last example. So now we have a cosecant of theta plus 1 equals a cotangent of theta over a secant of theta minus a tangent of theta. So definitely a busy problem. And I would say that the right side this time probably looks more complicated than the left side. So we have to find a way to make it not be so complicated. Well, it would kind of be nice if instead of a secant of theta minus a tangent of theta, remember we have a Pythagorean identity that has secants and tangents in it, right? It would be nice if it was a secant squared theta minus tangent squared theta, because that's a Pythagorean identity. So how can we make that happen? Well, we're going to leave the left side alone, but we're going to multiply the numerator and denominator by, well, we're going to make this a difference of squares. We multiply the numerator and denominator by the secant of theta plus the tangent of theta over the secant of theta plus the tangent of theta. We've multiplied by 1, and that's going to change things for us because now in the numerator we will have a cotangent of theta times the secant of theta plus tangent of theta. But in the denominator, so this is just multiplying by 1. But in the denominator now we'll have a secant squared of theta minus secant tangent plus secant tangent is gone, so minus tangent squared. And from our Pythagorean identity, the secant squared of theta minus the tangent squared theta should be a plain old 1. So our denominator is going to become 1 by a Pythagorean identity. So we're still trying to get a cosecant of theta plus 1, but now we've eliminated the denominator, it's plain old 1, and let's distribute our cotangent of theta times everybody. So we'll have a cotangent theta times a secant of theta plus a cotangent of theta times a tangent of theta. Oh, wait a minute. Aren't tangent and cotangent reciprocals of each other? So cotangent is 1 over tangent. If I take 1 over tangent times tangent, I should just get a 1 here. Does that make sense? And so this is simplifying. And we're still trying to get a cosecant of theta plus 1. Ooh, that's good because we're going to have the plus 1. So we need to find a way to make cotangent theta times secant of theta become cosecant of theta. So it may not hurt to change everything to the sines and cosines, if that makes sense. So we could use the quotient identity to make cotangent the cosine of theta over the sine of theta. And we really should do one more step here since we have room. And let's make the secant of theta using the reciprocal identity into 1 over the cosine of theta. So cosine of theta hasn't changed, sine of theta in the denominator hasn't changed, the plus 1 hasn't changed, but we did change the secant of theta to 1 over the cosine of theta. And finally, cosine over cosine is going to simplify to a 1. That's just simplifying. And we can also use the reciprocal ID. 1 over the sine is the same thing as the cosecant of theta plus the 1 that we had from before is going to be equal to the cosecant of theta plus 1. So again, we should probably split that down into 2 separate steps, but I wanted to give you plenty of examples and kind of ran out of space. So I hope this helps. Please repeat, rewind, go back, re-listen, try it on your own, stop, pause the video if you need to, see if you can figure things out. Maybe you can find an alternate way to do one of these problems.